what happened if you, for this one, phase 2? Okay, we need to, okay, we can just click output. Okay, here is after we install and also some loading there, 5 kilonewton per meter. The structure you see from this side now move downward. Before this, no. The soil just moved to the left, something like that, something this one. But now we have some load, which is 5 kilonewton per meter. So the geometry now become like this one. And if we look at the displacement, if we go to the shading, we can see this is now the displacement. We see with this loading 5 kilonewton per meter, we have about 19 meter and 19 millimeter, about 2 centimeter, somewhere around here, because of the load, but it is protected by the reinforcement here and also geogrid. Okay, so this is how we analyze our structure, or in this case slope. We can go to the effective stress and maybe we look at the mean shading, so we can see. And we can also, let's say we can click at the geogrid, see what happened there. Let's say we want to see the axial force, not much, deformation. Yeah, this one displays there, horizontal, vertical displacement. Okay, that geogrid is displaced about 8 millimeter, this side, and this one is 0. Okay. If we want to know what happened to this reinforcement, we can double click it. The same thing, it shows us the bending moment of that reinforcement. And we can see also the axial force, how much. This is axial force, shear force, and so on. So you can get the value here. Okay. I can just close this one. Okay, that is the analysis for elastic deformation. Okay, let's say now we want to know what is the factor of safety. Maybe we can create another one. Okay, this one we want to know factor of safety using 5C reduction method. Remember our problem, we need to find the factor of safety. So we choose the 5C. Okay, in this case, if we look here, phase from 3, so meaning that phase 3 start from phase 2. Okay, meaning that after this one, so it is analyzing this one, the phase 2. Okay, we want the first case, phase 1, as well as phase 2. What is the factor of safety? Okay, in this case, we can just use the phase 1 and then phase 3. Okay, and then we have a next one. This one, click here, 5C reduction to get factor of safety, but from phase, not phase 3, but phase 2, from phase 2. Okay, so phase 4, this one is actually analyzing the phase 1. From the phase 1, okay, or phase 2. This phase 3 is for this one, phase 1, factor of safety. Phase 4 is for phase 2, factor of safety. Okay, now we can just do the calculation. Okay, it is running now. And you can see here, safety factor here, MSF here, it is 1.8. But this one, since there are so many steps, it go and it can go down or it can go up. So the value of safety factor here. So this is a safety factor. Okay, we are waiting for, actually it's taking time, because the number of elements a lot, we use the find, and my laptop also not the latest one, it's not even i3, less than i3, so it still you can still run the Fluxys. So now current step is 75. Maximum step is 117. We have the number of element 446 here. So safety factor here until now it is safe, 1.8. Okay, we just wait for the result. So if you have a good machine, for example, i7 or i5, it's just like a blink of your eye. You're gonna get the result, maybe. I don't know. But because this is quite an old system, okay. Now for phase 2 now, for the second one, the first one done. Now the second one, for the second geometry, with the reinforcement as well as the geogrid. Okay. So the same thing, it seems the factor of safety is good, 1.8. Okay, we just wait. And we still have a few minutes time left. So I'm using the one that I the Fluxys download using the get into PC. It seems it's running, no problem. But the tricky part is for the installation. You need to follow the video really like step by step. Okay. So it is done. See factor of safety. Okay, for the first one, to know where the factor of safety, you go to multiplier. So this is the value of safety factor, 1.86. For the first one, without any geogrid, reinforcement, as well as the loading, 5 kilonewton load. The second one with the loading is 1.84. So meaning that the slope here, it is stable. It is stable. The slope is stable. Okay. So yeah. So you can just say since the factor of safety 1.84 is stable. Okay. If we go back to our input, so you pop up, it will pop up like this one. I just choose learn fluxes. Okay. Okay, so now if we look at the material, okay, I just want to check. Okay, the sand here, actually we can change the color. For example, like this one, I double click at the lesson one. Let's say I don't like to put the name of lesson one. Let's say I say sand. And then I want to change the color. Okay, like this one. So the color change, and I can also change the name, and I can also change the gamma, unit weight of water, soil. So normally this is saturated. This is the unit weight when we get the sample, meaning that at site this is the value. This is the value. If we look here, the K is permeability. For sand, normally we put 1 meter per day. If we look here, this is the Young modulus. You can get it this value, the typical one, or you can do the consolidation lab test. For consolidation, you can get this value. And also no is Poisson ratio. If you learn strength of material, you know. For soil, it's about 0.3, 0.25, 0.35 around that. And cohesion here, because sand is about 1. Normally we don't put 0 because sometimes we worry it will have the issue of divided by 0. So the calculation go haywire. So we put at least 1 or 0.1 so that the calculation give result. And the phi value, angle of internal fraction 31. Yeah, that is quite high. So that's why the structure, the soil, okay. And we don't have interface. If we have interface using this one, we need to change here the interface. Since we don't consider interface, we don't worry about that. Okay, so this one we can double click and maybe just give a name clay. And then we can change also by okay color. Okay, for the clay here 16, 18, okay. If you look here, because it is clay, they're using a 0.00001 meter per day, because clay, the K value is very low, so they just use 0.0001. And then E value is about 10,000 kilonewton per meter square, which is quite low because it's clay. No, it is Poisson ratio is 0.35, C5, phi 25. So I think it's okay. That's why they're using quite a strong soil. So that's why it is okay, meaning that factor of safety 1.8. So that is how to analyze. Okay. I think it's about time. Okay, but I can show you another problem which I'm currently working on. But this one you can say off record. Okay, I have we have still have about time. I just run quickly, maybe 3 minutes. Just to show you the project that I'm working now. Okay. Okay, so let's say can I okay. Okay, this is somewhere in Kuala Lumpur after the flood, the flash flood. Actually, this is a hilly area. You can see here the foundation. This is the pile foundation actually being exposed by the landslide or slope failure. So I was supposed to do some forensic analysis to this problem. So I need to get the geometry and so on. Yeah, okay. If you look here, actually there is a pile here. Exactly here is off, off like about 1 foot off, meaning that the pile is hanging. So the left side of this 7 story building, actually the foundation here, they are hanging, meaning that it become a cantilever. The pile cap is not working as well as the foundation. So the load here is being distributed to the other pile, which is somewhere here. So this is what happened. So this is the slope failure. So I need to study whether how to do some improvement to the slope as well as the building. So what I did analyze using Fluxys. So I study the whole structure. Actually, it is here. The building is here. So we need to rectify or make the pile working again. But I'm studying the slope here. They're going to have like access area here, a big drainage, and a gabion wall here. This is a global stability analysis. That's why it's taking stretch the geometry. So gabion wall here, and this they are using a soil nailing, like using the nail. Actually, it's a steel reinforcement. This is steel reinforcement. They call it soil nailing. And then when I studied this whole structure, it seems I can divide the problem into two issues here. Because here the deformation is very low, so I can analyze this one separate than this one. So I do some, this one I'm using the slope W software to find the factor of safety. So because slope W, we can see they're using the limit equilibrium method, which I think you also learned in your, I think in the previous course. This one is using slope W. It gives 1.7 using Morgenstern method. So actually here there are so many failure envelope, but this is the critical one. The lowest value is 1.7, so it is safe if I design something like this one. Okay. And because they want to install, one machine need to come with a 30-ton machine so that they can rectify the pile. So 30-ton machine will be here. So still we see here without the reinforcement it is only one. So this one is not enough. It's not allowed. It must be at least 1.5. So this one we cannot. That's why we need to do reinforcement here. And when we do the reinforcement, we get 1.6 with 4 layers of soil nailing. So yeah, this is what's going to be done. They're going to install soil nailing. Okay, this is one of the sample problem using finite element, Fluxys as well as slope W. Okay, I think the time is up. Okay, you can, yeah, maybe if you want to ask me, I allow for 1 minute. If not, then we can dismiss. And I hope it helped you to give some idea. I don't expect you to do this quite heavy analysis. This is a real problem. For you, maybe get some picture to get some idea of how the geotechnical engineer works, get the geometry and run some analysis, got the result, and then discuss the result whether it is okay or not, and check for factor of safety. Make sure it is greater than 1, meaning that it is stable, but preferably above 1.5. Even some they are using above 1.25. Okay, I think I would end up our meeting here. Yeah, any question? Maybe some, I don't know. Or are you all still there? Or okay, yeah.
Can I ask you something?
Yeah, sure.
For the report part, we need to show manual calculation or not? Just what doctor say we only need to
Okay.
do software analysis. So I just
Okay.
want to make sure.
It is good if you do the manual calculation. Just check for the simple one. For example, what is the stress? Easy calculate, right? Stress equal to the depth time unit weight they are using. Okay, for example, I show you. Okay, like this one. What is the stress here? For example, this one. We have like, okay, let's see here. About 12 meter height. We have this one is 12 minus, I don't know here, about 4 or 5 meter, 3 meter. And then times unit weight they are using here, plus this height times unit weight they are putting in the material properties, and then you get the stress. So that is one of the way to check. It's simple one. So even for poor water pressure also, it will show you. It is good if you check. Otherwise, we don't know. We just it could be garbage in, garbage out. Okay. Yeah, don't do the full analysis manually. Especially this one is not for that. For slope W, you still can do manual calculation, but for Fluxys, maybe you can calculate the stress because easy calculation. What is the stress at the bottom here, the highest? You can calculate easily. And then you check the one that Fluxys give, more or less the same. So that is one of the way to check. Or maybe the groundwater level is here. So to check for water pressure, you know this height time 9.8 or 10. So you get the value of water pressure. You check with the Fluxys, is it the same? So simple checking. The rest, I don't expect you to check because finite element is a very tedious, long calculation if you want to do manual calculation. And I think you are also not equipped with that. It is in the postgrad level for this one. I hope that answer your question. Okay.
Yes, thank you, doctor.
Okay, any question, or maybe we can just dismiss our meeting? Okay, time is, I think 10 minutes. It's not good for me to delay. Okay, we can we meet again on Thursday, 4 o'clock as usual. Okay, inshallah.
Okay, thank you, Doctor.
Okay.
Thank you, Deh.